For a time, the electromagnetic railgun looked like something ripped straight from a sci-fi blockbuster. No gunpowder, no explosives, just raw physics hurling a metal slug at 7 times the speed of sound toward a target up to 200 miles away. The US Navy pitched it as a revolution in naval warfare, cheaper ammunition, pinpoint accuracy, and safety benefits that could change the game forever. The story began with enormous promise. It ended in 2021 with an expensive reality check, a trail of cracked test rails, and 0 operational deployments. This is the tale of how the railgun soared on hype, stumbled on hard engineering, and lost the race not to the laws of physics, but to faster moving alternatives. The spark that started it all. The railgun's basic principle isn't new. Over a century ago, in 1918, French inventor André-Louis Octave Faucon-Villeplay built what was arguably the first electric cannon. His design used electromagnetic forces to accelerate a magnetic projectile to high speeds. In theory, the concept was straightforward. Pass a massive electric current between 2 parallel conductive rails with a sliding projectile in between. The resulting Lorentz force pushes the projectile forward at incredible velocity. In practice, it was like trying to bottle lightning. Early designs remained laboratory curiosities, powerful but impractical. German engineers during World War II sketched an electric anti-aircraft gun, but it never left the drawing board. For decades, railguns lived mostly in military research papers and sci-fi novels, a tantalizing what-if that seemed just out of reach. The Pentagon's big bet. In 2005, the US Navy, always hunting for the next revolutionary weapon, decided it was time to bring the railgun from theory to battlefield reality. With backing from the Office of Naval Research, the vision was bold, a gun that could fire projectiles at Mach 7, around 5,370 miles per hour, strike targets over 100 nautical miles away, and do it without explosives, relying purely on kinetic energy. The advantages were clear. No existing naval cannon could rival that combination of range and speed. For perspective, the Navy's reliable Mark 45 5-inch gun, in service since 1971, could reach only 20 miles. Even the colossal Paris gun of World War I managed about 81 miles, and modern long-range artillery like the M1299 howitzer topped out at 68 miles. By early 2008, confidence was soaring. A prototype from BAE Systems set a new record in a Virginia test, prompting the Navy to raise its range target to 200 miles at Mach 7. The sleek 𝐬𝐮𝐬𝐫𝐞 destroyers were tapped as the first ships to carry this wonder weapon, with sea trials slated for 2016 and full operational deployment to follow soon after. At the time, it seemed like the future of naval firepower was just over the horizon. How it works, and why that's a problem. At its simplest, a railgun is an enormous electric circuit shaped like a gun barrel, consisting of 2 parallel rails, a conductive projectile, and a surge of electricity. In the Navy's case, millions of amps per shot. To put that in perspective, an old incandescent light bulb draws about 1 amp, a phone charger between 1 to 5 amps, and even a high-powered gaming PC under heavy load only needs 5 to 10 amps. A railgun demands 1 million, requiring massive capacitor banks or advanced alternators that take up huge amounts of space and weight. Only a few ships in the fleet, like the 𝐬𝐿-class destroyers, could generate enough power to even consider operating one. The physics behind it were nothing short of astonishing. A 10-kilogram slug launched at Mach 7 would hit with the kinetic force of a cruise missile without using explosives. That meant ships could carry far more rounds, no powder charges or heavy shells, and avoid the catastrophic risk of ammunition magazine explosions. On paper, it also promised to act as a low-cost missile defense, able to knock out aircraft or incoming missiles for a fraction of what traditional interceptor rockets cost. Hype meets hard reality. As impressive as the railgun sounded on paper, the engineering challenges proved far tougher than expected. The first issue was barrel life. At Mach 7, the heat and friction inside the barrel were intense enough to erode copper rails, vaporize metal, and create extreme pressures. Test rails often cracked or warped after only a few dozen shots, and even stronger alloys or advanced coatings couldn't deliver the hundreds of rounds needed for practical use without major repairs. The second problem was rate of fire. For missile defense, the Navy wanted 6 to 10 shots per minute, but in reality, the huge capacitor banks required long recharge times, often a minute or more between shots, just to prevent damage to components. That slow pace made it ineffective against fast, swarming threats. Finally, there was guidance and accuracy. A projectile traveling at Mach 7 needs onboard electronics to hit moving challenging targets, but packing guidance systems into a shell that can survive 40,000 to 60,000 Gs of acceleration and searing plasma heat proved extraordinarily difficult. By the late 2010s, the Navy had already poured more than $500 million into railgun research, and making it fully ship-ready would demand hundreds of millions more, with no assurance it would ever work as promised. The world takes notice. As the US struggled to overcome the Railgun's technical roadblocks, other nations were quietly advancing their own programs. In 2018, China caught global attention when images emerged of the 𝐻𝐿 a converted landing ship sporting what appeared to be a massive railgun turret. US intelligence suggested it could fire at full power and strike targets more than 120 miles away. By 2023, Chinese researchers claimed a major breakthrough: 120 consecutive shots at Mach 6 without significant barrel damage, credited in part to an AI-driven diagnostic system monitoring over 100,000 sensors. Meanwhile, Japan launched its Railgun initiative in 2016, aiming to counter hypersonic missile threats. By 2023, Japanese engineers matched China's 120-shot endurance milestone and achieved the world's first modern shipboard railgun firing. India also entered the race, testing smaller prototypes before opening a dedicated electromagnetic launch systems center in 2025 to develop naval and high-altitude border defense applications. Europe has taken a slower, more methodical route with the EU's Pilum project 2020 to 2023, focusing on feasibility studies and planning a full-scale demonstrator by 2028, with possible deployment by 2035. Despite the US program's collapse, the railgun remains an engineering holy grail, an irresistible challenge many nations are determined to solve. Why the US walked away. The end came quietly. In July 2021, the Navy announced it would pause railgun R&D at the end of the year, citing budget constraints, integration challenges, and the rise of other weapons. The death blow was the cancellation of the hypervelocity projectile program in the 2022 budget. The real reason? The railgun wasn't just competing against physics, it was competing against better, faster maturing alternatives. Missiles and lasers leapfrog ahead. As railgun development stalled over cost and technical hurdles, hypersonic missiles and shipborne lasers advanced rapidly. Missiles grew more accurate, longer ranged, and cheaper per effect, while lasers like the US Navy's 60-kilowatt Helios, the UK's Dragonfire, and China's ship-mounted systems moved into service. Lasers offer speed of light engagement, virtually unlimited shots, low cost, and pinpoint precision, advantages railguns never matched, making them the more practical near-term weapon. Two possible futures. The railgun story leaves history with two diverging possibilities. In one scenario, the US is vindicated. Other nations pour billions into chasing the same dream, only to encounter the same insurmountable engineering challenges and ultimately abandon the effort. In the other, it becomes a cautionary tale. A decade from now, another country finally cracks the technical code, deploying a functional railgun while the US stands on the sidelines, regretting that it pulled the plug too soon. For now, the Navy has shifted its focus to missiles and lasers, leaving the railgun as a high-profile casualty of modern military R&D. A reminder that even the most dazzling futuristic concepts can collapse under the sheer weight of cost, competition, and cold reality. And that's the rise and fall of the US Navy's railgun, a story of big dreams, bigger budgets, and even bigger challenges. If you enjoyed this deep dive into military tech, make sure to hit that like button to let us know. Want more fascinating stories from the edge of science and defense? Subscribe and turn on the bell so you never miss an upload. Got thoughts on whether railguns still have a future? Thanks for watching, and we'll see you in the next video.